Hello, I'm Haddadi. I'm a faculty at Imperial College London. I will briefly talk about some of the recent projects that we've been working about in the space of personalized and privacy-preserving analytics. Specifically, what my group works on is design and release of open source systems and tools for human-centered applications and personalized analytic services, which obviously aim to respect the individual's privacy and security. Over the last few years, we've been specifically working on the DATABOX platform, which is a large open source platform which enables local analytics to be run. And while containing these different applications, so specifically you have containers for different applications, different data sources, and you can do analytics on an edge device across different data sets, while not allowing these applications, for example, or the data sources to be able to infer the other, to infer much about sensitive data sets that are residing on the user's device. So this doesn't stop you from sending data to the cloud. What it does is that it allows you to aggregate and do analytics across various data sources that usually they're not available at the same operator or service provider. Specifically things like model, for example, personalization, where you have a pre-learned global model that you can, for example, use a very simple two-layer network. And on a device, for example, here we are looking at activity recognition. Using few minutes worth of data, you can take a pre-trained global model with just less than 60% accuracy, and using about just over 2 minutes worth of data, you reach about 80% accuracy in activity recognition, while the model is completely running on a handset or, for example, an edge device like a Raspberry Pi. And this only takes a few seconds worth of inference time, so and training time. So it's not actually, these are not heavy and big models. But specifically looking at big models, we've been looking at can you, for example, allow some sensitive applications to run and perform some primary tasks, but kind of block against the other tasks being able to run. For example, if a shopping mall or some smart city service wants to do customer surveying or tasks like understanding the age of individuals in a mall, while you want to prevent face recognition, can you do that easily? So for that, we've been looking at, for example, layer separation, specifically where you have, for example, convolutional layers running on an edge device and fully connected layers running on the cloud. That allows you to, in a scalable manner, run specific applications locally while preventing sensitive inferences to be done on data that further on you transmit to the cloud. And this is a system that we've been working on for the last few years. Specifically, we've been looking at what kind of things you can run on the client side and what features do you leak back to the cloud, and how do you quantify the private features that are leaving your device. For example, here we've been looking at face recognition versus tasks like, for example, gender recognition and things like that. You can still achieve 90% plus on your primary task while using simple techniques locally. You're really reducing the ability to do accurate, for example, face recognition down to 2%. And more importantly, recently we've been looking at putting basically federated learning models into the trust zone. In a way, can you provide model privacy? So there's data privacy, but there's also sometimes sensitive models that are getting embedded into our devices, and we want to avoid for membership inference attacks, for example, or model reverse engineering of models. So what we've been looking at recently in a paper this year again is quantifying how many layers can you put inside the trust zone, how many layers can you have outside, and what's the effect of this in preserving the, for example, private information of those individuals who took part in training the model. And specifically, we can see that obviously we only can trust the layers of the model which are inside the trust zone, but we can see that these are actually really scalable. So it doesn't actually increase the load in terms of memory and CPU on the device at all, but it provides a high level of privacy for the models that we are keeping for both the inference and training tasks locally, and for applications like CIFAR 100, relatively big training sets and models. So this is quite interesting. So we've been further looking at further applications. For example, looking at, can you now bring these models into users' homes, looking specifically at sensing applications at home and federated learning applications in the home environment. We've been getting ready to deploy DATABOX across hundreds of care homes in the UK as part of a big grant on dementia research. And the aim of that has been performing tasks like model personalization and federated learning across these households in order to understand and be able to establish the behavior trends from the early onset dementia patients, while obviously respecting their privacy and those of the others living in their households. Specifically looking at activity recognition, we want to look at the trends that they have in their activities from a variety of IoT devices that are deployed in their homes. So even from devices like cameras, which could be potentially privacy intrusive. So specifically, we've been looking at models that can run even on a simple device like a Raspberry Pi, looking at cameras, smart plugs, temperature and motion and light sensors. And we've been looking at getting this data and then training, performing inferences across this data for doing model recognition. And we get quite good results with different data sets that we have. And then we've been simulating for now, because we haven't completed the deployments yet, of releasing these data sets back into the cloud for training the public model. So specifically, this also has some issues in terms of defining the privacy policies, and my colleagues Minos and Eugenie will now talk about applications of federated learning for privacy policies.
Hello, I am Cleomenis Katevas. I am a researcher at Telefónica Research in Barcelona. I will talk about our ongoing work, which is PoliFL, a federated policy-based framework for personalized and private data analytics. Traditional ML-based systems tend to follow a common pattern. Data are collected from various data sources, then aggregated and processed centrally, typically on some kind of cloud-hosted service. While federated learning tries to solve known challenges such as trust, security, and scalability, the idea of decentralization raises new data access challenges, as users are still faced with an all-or-nothing data access decision, that is, either unrestricted access to the data sources or strict denial of access that often means denial of key features of the application. To motivate this talk, I'm going to mention one of our past works. We built an LSTM-based classifier that could detect whether a user will react to a received notification within 10 minutes of receiving it. The data sources that we used are listed here. Even assuming a federated learning fashion for training the classifier, it also means that the user will need to trust a third-party app with access to all these sensitive data sources, including the microphone for measuring the noise level, or the location sensor for inferring the semantic location of whether the user is at home, at work, etc. Here we highlight some limitations of federated learning in the context of this work. Users still need to trust the provider's FL code execution on their devices. Some users want to build models only for app A, but not for app B. Some users might choose more or less privacy, maybe even want to share the data directly with the global server for training over there. Yet this is impossible with the current design of traditional federated learning. Here we present PoliFL, which is an open source federated policy-based framework where all local data accessed by the FL code is controlled by a policy. It uses Untitled Policy Management Framework to impose restriction on data usage using the concept of use-based privacy that defines privacy as a prevention of harmful uses. Users have control on how their data are processed and shared. It is built atop of DATABOX as a secure platform to store all user data. This is a simplified version of our PoliFL architecture. Central service is responsible for receiving data processing requests from third-party services. It handles these requests by coordinating with the edge devices that contain the data. The central service transfers the request along with the associated data policy to the participating user's DATABOX, where data are accessed and processed locally in accordance with the data policy. In this work, we can assume that each user has deployed an edge device, for example a smartphone, that stores all sensitive mobile data mentioned earlier. A service wants to build a classifier that detects whether a send notification, for example a pizza voucher, will be opened by a user within 10 minutes and does not have direct access to the collected data. Instead, it uses the central service to distribute a use-based policy for execution on the edge device, optionally with a shared model. Untitled framework executes the policy at the edge device. In our case, train the model locally, returns the model back to the central service, and apply the required federated aggregation. After the required training rounds are completed, the model is returned back to the service. As mentioned earlier, each user has their own policy associated with their data, and different policies can be combined together. In this example, we saw a generic policy for FL training with differential privacy enforced. We use regular expressions to control concatenation and union for processing functions. The first part of the policy allows to fetch the data, then requires to perform local training with differential privacy, and finally send the resulting model to the server for accumulation. The rest of the policy controls what happens with the model afterward, on the server or when it's sent to the other users. We evaluated PoliFL on different training strategies. Image classification doesn't suffer from using federated learning, whereas language modeling benefits from centralized training. Differential privacy impacts more the language model than the image model. We also report a mixed strategy, with some users train their data locally and some others share their data to train at the central service. To summarize, we presented PoliFL, an open source federated policy-based framework that mediates third-party services to an individual personal data via verified, audited, and policy-controlled programs. It is open source and available in GitHub under AGPL license. The draft of this work is available on arXiv, and in the future we want to integrate with TensorFlow Federated. Thank you.